So here we have a differential equation, dp dt equals kp times 1 minus p over m, where the maximum carrying capacity is m, and this is a logistic model for population growth. Here I'm gonna walk you through how you can derive a general solution for this differential equation. So first, let's start off by separating the variables. Let's rewrite this as k over 1 over p times 1 minus p over m. So we can use cross multiplication and integrate on both sides. So the integral of 1 over p times 1 minus p over m dp equals the integral of k dt. And the next step is rewrite the 1 as m over m, so we can subtract this fraction and make it a single fraction, so that becomes 1 over p times m minus p over m equals to k dt. And then we want to multiply the top and bottom by m, so we can get rid of the m on the new denominator. So this becomes m over p times m minus p dp equals the integral of k dt. So from here, we can use partial fraction decomposition, which essentially states if you have a fraction that's like this, then this is equal to a over p plus b over m minus p. So this integral becomes the integral of a over p plus the integral of b over m minus p. And to find your values for a and b, you just write it as a times n minus p plus b times p and set it equal to m, because if you were to add those two fractions, you would multiply your a with this denominator, and then you would multiply your b with this denominator. So my strategy for solving for a and b is, if you were to solve for a, plug in a value that will make the b term 0. And if you were to solve for b, plug in a value that will make the a term 0. So in this case, let's let p be 0. So am equal to m, a equals 1. And if we were to solve for b, let's let p be m. So this term will be 0. So we have bm equals m and b equals 1. So once we have our a and b values, we can continue with our integration. So this becomes 1 over p plus 1 over m minus p equals k. And of course, 1 over p is just ln of the absolute value of p. And here, though, we're going to be careful. Although here we have a plus sign, but the solution to this is actually a negative ln of m minus p. The reason for that is, if you let u be m minus p, then your du will be a negative 1. Right? So to accommodate for this minus 1, you will have to have an extra minus 1 outside. So that will make this a negative ln of n minus p. And that is equal to kt plus c, because k is a constant and we are integrating with respect to t. So this becomes kt and plus your constant c. So, and we can use one of the logarithm properties. When you subtract two logs and they have the same base, you can write it as a quotient, and that is ln of p over m minus p equals kt plus c. And to get rid of the ln, we can do e raised to the kt plus c. So p over m minus p equals c times e to the kt. So here, though, because e to the kt plus c is the same as e to the kt times e to the c, right? That's one of our exponent properties. And e to the c is also just some arbitrary constant c, so we can rewrite that as c times e to the kt. Okay, so now let's flip everything. So if we flip the left side, we'll have to flip the right side. And if we were to flip this, let's think of this as 1 over c times e to the kt, or 1 over c times 1 over e to the kt. And because c is constant, so 1 over c will also just be some arbitrary constant c times 1 over e to the kt, right? Yeah, kt. That's kt. So this is the same as c over e to the kt, so which is what we have right here. And then we can multiply both sides by m. So m minus p equals p times c over e to the kt. And m is therefore equals pc over e to the kt plus p. And from here, we can factor out the p. So m equals p times 1 plus c over e to the kt. And to get p by itself, we just divide both sides by this piece. So p equals m over 1 plus c over e to the kt. And that is how you derive the general solution for this differential equation.